Let's make a start. Awesome. So this one is going to be a kind of lesson where going to be very collaborative in this one because we're going to be looking at the index laws in the context of exponentials and logarithms. I could just show you all of the index laws. That will take me all of 5 minutes. Much easier instead to see how you actually use them in the context of simplifying things. So here they are. These are the index laws. We'll be using all of them at some point. And if you haven't already done exponentials stuff, the closest thing you have to having done this before is polynomials, when you'd have like x times x squared giving you x cubed. That's what this like index law 1 is talking about. Same thing with division, right? When you had x squared divided by x, you just get x. You subtract when you divide. We'll be having a look at how to use all of these during the lesson, as well as a few of the identities as well. So we're looking at stuff like whenever you have anything to the power of 0, that thing will always equal 1. That's just a consequence of how the index laws work. We'll look at negative indexes, the idea of how you can then flip those into fractions if that's at all easier to work with. And we also look at what it means to have a fraction as a power. That's more or less the agenda for today's class. So let's have a look. So in fact, what I'll probably do is, to make life a bit easier, I'll just drop the entire summary document in rather than doing a... Oh, actually, no, this can be a one-page screenshot, can't it? Nice, that's much easier, actually. So these are the index laws we'll be referring to. I'll pop that in the chat. And essentially we'll just go through the textbook and I'll do a few examples to start off with. If this is something you're already familiar with and you'd like to go at your own pace, then one of the things I can do is just drop my textbook solutions to the two ones that we'll have a look at, and you can just sort of go ahead and check your answers at your own pace. So it'll be 13A, 13B of the Cambridge Unit 1 and 2 book. Those will be downloading shortly into the chat. So if you want to go at your own pace, you can just refer to those. I've already done fully work solutions for all this stuff. Okay, let's have a look at a few examples. So bare bones basic stuff, we probably don't need to talk about anything like AC, B, or D. Around E is where things might be considered new. So let's have a look at what's going on there. So if we look at 1E over there, we have what I refer to as cascaded powers, or basically we have a term that is raised to a power that is then raised to another power. In this case, we have a to the power of 3, and then that is also raised to the power of 2. When you have this scenario of cascaded powers, you can simplify this result by multiplying the two powers that are involved. So when you have a to the power of 3 and then it is raised to the power of 2, that now becomes a to the power of 6 because you're doing 3 times 2. That's pretty much it. This also works if your base is not a letter but a number. So for instance, if a was 2, you would have 2 to the power of 3, power of 2. That is again going to be 2 to the power of 6, which is something you can then simplify from there. Worth pointing out, powers of 2, pretty important to be able to do rapidly, right? These come up quite commonly, especially in Unit 1 and 2, where looking at 2 to the power of 6, you're going to want to be able to do your powers of 2 pretty quickly, like 2, 4, 8, 16, 32, 64, bang. We know that this is going to be 64. Now, if that repeated doubling isn't supernatural to you, there's a really fun way of practicing this, and it's because you get to practice it by playing a game, 2048. I don't know if you've played in cool math games or if that's still around. It's a game where you just essentially join numbers of 2 together, and by doing so, you'll see all the powers of 2, and you'll have a bit of fun. So that's the most fun homework I could probably assign if you're at all interested in being able to rapidly understand your powers of 2, which is a decent skill to have. But okay, that's that index law. When you have those cascaded powers, the powers multiply. The other kind of thing that comes across is being able to distribute powers. So in the case of G, in fact, what I'll do is I'll just copy them all down onto my handwritten notes section so you don't have to keep clicking back and forth between tabs. So if we have a scenario like this, x, y, all to the power of 2, when two things inside brackets are multiplied together, and then those brackets are raised to a power, what you can essentially do from there is distribute that power to each term. X squared, y squared. It distributes between both. If they already have powers, then you're essentially using two separate index laws. So for instance, if I had x squared, y cubed, all to the power of 2, once again, I'm going to distribute the 2 through to both of them, and that's going to end up looking like x squared power of 2, and then y cubed power of 2. This one should now be familiar at this point, because you've got powers raised to powers. Those are going to multiply into each other. So you've got x4, y6. So you're essentially making use of both index laws in that circumstance, but the fundamental is still the same. You had two things that were multiplied together that were raised to a power. That power can be distributed into each individual term. That is also the case for division. So if instead of having x times y, I had x divided by y raised to some power, let's say 3 this time, then once again I can distribute that into the top and bottom of my fraction. X cubed over y cubed. And finally, if those also had powers associated with them, x squared, y cubed, we'll say power of 4 this time, then you once again have a scenario where you've got cascaded powers. You've got x squared, power of 4, and then you got y cubed, power of 4. Those cascaded powers you then multiply through into each other. X power of 8, y power of 12. That's about it for those fundamentals. The other is a real quick one. If I have any number, let's just say 8, and it's the power of 0, you're always going to get 1. I don't really know how else to show that on its own. You just sort of have something to the power of 0, and it equals 1. That's all there really is to that. Negative indexes is where things get a little more nuanced. There's a couple of things I can show there. Basically put, the whole point of a negative index is that it can always be flipped on itself. So basically 1 divided by whatever the number is, you flip. So currently we have 7 to the power of negative 2 there. This is the same thing as 1 divided by 7 squared. So essentially the rule is, if it'll stop blurring, the rule is that you do 1 divided by whatever the number is, and then you change the power from being a negative to a positive. That's the rule. Now, what happens when you have a fraction that is raised to a negative index? Let's say it's a quarter to the power of negative 2. You're still doing 1 divided by this number. So 1 divided by a quarter ends up getting it down to 4. And then you swap that negative 2 to a positive 2. That's pretty much it. So a quarter power of negative 2 ends up being 4 squared. If this was, let's say, we'll even do a separate one. If we had 3 over 4 instead, power of negative 2, once again you're still doing 1 divided by this thing, which in this case would make it 4 over 3, power of 2. Negative goes positive. So in all cases, you look at whatever the thing is, the base, rather than the exponent, the base, and you flip it 1 over itself. Then you flip the negative index to a positive index, and you go from there. Like this one, for instance, you could then distribute if you wanted to. This is 4 squared over 3 squared, which then obviously simplifies to, what's that, 12 over 9? 4 4s are 6, no, 16 over 9. a lot of this is just going to be playing with index laws and trying to get it as simple as possible. Let's see, did I hit all of them? Did that, did that, did that. The last one we'll look at is the rational index when you have a fraction. So the way fractions works is that they're actually square roots. Well, more specifically, just any kind of root. So I'll talk about it generically and I'll show a few examples. If we have any a to the power of, I'm just going to use b over c because those are probably a bit easier to distinguish between. A to the power of b over c. That is the same thing as the cth root of a to the power of b. So basically the way that works is whatever the denominator is the root of your index, and whatever the numerator is the power of the base. This is probably the nicest way to write it, but it's inversely the hardest way to actually solve it. Usually it's easier to do the cth root of a and then raise that to the power of b. And we'll see why with an example. In fact, yeah, let me see if I can find a good one for it. Yeah, okay. This will do. So if we go with 125 to the power of 2 over 3, one potential way we could write that would be this first example here, which would be the third root of 125 squared. The 3 is there, making it the third root. The 2 is in the numerator, making it the power of the base. Now here's the thing. Who knows what 125 squared is? I couldn't do that off the top of my head. That's a lot of effort. So instead of doing that, we can rewrite it in a bit of a different way, because it doesn't actually matter what order we do these in. We can power first, then root later, or we can root first and then power later. If we root first, we're working with a lot smaller numbers. So cube root of 125, that's much easier. Assuming if we assume that it's always going to be some form of integer, it doesn't take much time to test what that could possibly be. Cube root of a number just means 3 identical numbers that multiply together to give that thing. That's going to be 5 in this case. 5 5 is 25, and then 25 times 5 gets you to 125. So all of a sudden, we've taken that nasty big number down into just 5 squared. Much easier than having to do 125 squared and then trying to square root whatever that ends up being. In fact, just out of curiosity, let's find out what is 125 squared. Yeah, there you go. 15,625. So good luck trying to cube root that. You can do it, obviously, through guess and check. But guess and checking your numbers up to 25, probably not going to work out too well. Yeah, so recommendation, pretty much you'll always be using this version of that way to simplify things, because smaller numbers are better than bigger numbers as far as working with them by hand. If you're doing CAS, obviously none of this matters. You can just CAS it out and you'll be sorted. But yeah, I've yet to see an example where doing it this way is better than this way. We've gone through pretty much all of the individual circumstances that can come up. Is there anything, or any one of those index laws you can even refer to? I'll pull up on the chat, on the screen share, what all the index laws are. Is there any one of those individually that don't make a whole lot of sense and you'd like me to go over in a bit more detail? Easy. All right. Well, this is where we're going to throw it back to you guys, because now we're going to do it collaboratively and go through these. So let's see, where's a decent starting off point? We'll call it 2D. You don't have to really refer to the textbook if you don't want to. I'll write down all the ones that we're doing. 5a cubed b squared times 6a squared b to the power of 4. Alright. Well, maybe you do have to refer to the textbook if it's not going to stop being blurry. My god. There we go. Cool. Alright. I'll throw it back to you guys now. What kinds of things can we do to simplify this? There's no solving as such, more so just trying to get it down to its simplest form. 30a power of 5, b to the power of 6. Yeah, cool. Exactly. So essentially what's going on there is the two numbers can multiply together because, well, it's multiplication. 6 5 is 30. And then we're using the first index law, which is when you have two indices multiplied together, the powers add. So we got an a3 and an a2, that makes an a5. We got a b squared and a b4, that makes b6. Cool. Alright, that was a fairly chill one then. Let's have a look at a bit more complicated. Let's introduce some division into the mix. And by the way, if I'm doing a question and you'd like me to clarify anything, I'm more than happy to go back on a question. So just shout out, happy to have a look. 8a squared b times 3a5 b squared divided by 6a squared b squared. 6a squared b squared. Bit more involved there. We're going to be using more than one index law associated with this. There is a preferred order to doing these things, I'll say. There's a few ways you could do it that could work out. 4a cubed b. I mean, probably. I can't see that immediately. Let's let me pull up the answers on that one. Might be easier if someone can walk through like each individual step that was done on the. Maybe you don't have to say like exactly what the steps look like, or what steps did you do the order in. Like, did you do numerator first and denominator? What were the sort of things you had to look at?
Chris, could I just quickly rectify my answer?
Oh, sure, yeah.
I think I was actually meant to say 4a to the power of 5 times b.
Okay. I mean, I still can't see what that's going to end up being, just by
And
having not done it before.
that's because
Yeah.
okay, so I was going like term by term. So you get a times 3, which is 24.
Yep.
And then a to the power of 2 times a to the power of 5 is a to the 7.
Yep.
And then b times b squared is b to the power of 3.
Yep.
And then if you put that all over 6a squared b squared, you just do the same process again, but in division. So
Mm-hmm.
24 becomes 4, and then 6 becomes 1. And then
Oh, yeah, yeah, yep.
a squared cancels out, and then a to the power of 7 on the top becomes a to the power of 5.
Yep, so that's the subtraction when you have division, yep.
And b to the 3 over b squared, like the b squared cancels out, and it's just b on the top.
That's it, yeah. So the preferred way of going about that usually is going to be doing your numerator first and denominator, which is basically how we've outlined it here. You have multiplication, so you're doing the adding of all the indexes, and then once you have division, you do the subtraction of all the like indexes. Certainly. Cool. All right, that's that one there. Let's see, what else have we got? It's a bit more complicated. Yeah, let's yeah, we'll kick it up to 6b. Why not? Let's have a look at what's going on in there. So we've got 5a cubed b cubed over ab squared c squared, ab squared c squared. All of that is raised to a power of 3. I'm sure it'll unblur eventually. Divide a squared b negative 1. Oops, cut that off too early. C, and then 3. Make that look 3. Cool. So a fair bit going on there, absolutely. We're now looking at, in fact, I think there's going to be 2 new things that we haven't touched on yet, which will be when you have powers and when you have negative indexes.
Could you just get rid of all the to the power of 3s?
Yeah, I would love to do that to start off with. That's usually the first thing I'll recommend in these circumstances, which is distribute those power 3s. Yeah. So the way that looks is everything in here is going to get a power 3. So 5 power 3 is going to get it. A power 3 is going to get it. Now remember, when you have power on power, it's a multiply, not an add. So we're going to have A9, then B9. Lastly, you're going to have A3 on bottom, B6, C6, because it's 3 times 2 in both of those circumstances. Same thing over here, which I'll let you say this one if you'd like. What does this simplify out to?
A to the power of 5.
Close. Remember, it's multiply when you have powers like that.
Would be A to 5 and then B to squared.
So kind of like how we did it before here, where there was power to power. It's a multiply into both.
Oh.
So this one here, you've got a 3 and a 2.
Oh, yeah, that's 6.
Yeah,
Sorry.
6. There you go.
6 then -3 then.
There you go. Nice. B -3 and then C 3. Nice. And yeah, like this is why we're doing this, right? Because there's so many little things to keep in track of. Do we add? Do we subtract? Do we multiply? Do we divide? In fact, I don't think I've seen. Is there a division? I don't think there is a. There's kind of a division of powers under some circumstances when you multiply by a fraction, but otherwise, yeah, pretty much just stuck here. Now, where it's left here is kind of nasty, in my opinion, because we've got a division symbol as well as a division line, like a fraction line. It's workable from this state. It's kind of tough, though. What could we potentially do to make this a bit easier to work with?
Could you get rid of the division before? I mean, not the division, the fraction before you do the division.
Get rid of the fraction. So as in try to simplify this left-hand side first?
Yeah.
Yeah, certainly. So what kinds of things could we do to simplify this left-hand side?
I was actually gonna ask, could another way to do it be you do like the numerator times by the inverse of the denominator?
Times by. So as in like flip all these up to have negative indexes?
Yeah, but is that like another way to do it?
Well, it's actually the same thing.
Okay.
So whether you flip these up to be negatives and then add negatives, or if you subtract positives, that actually ends up meaning the same thing. I actually do literally do it the way you just said, which is I flip these up, and then that's literally how I'll do it. I'll flip up everything in the same go. So I'll see this division, flip it up, see this division, flip it up, and then I'll have all one big line to work with. But that's because I can handle a lot of things at the same go. Usually what I find a lot of people find easier is to just sort of look in self-contained little sections like this. Like we see an A9 up here, we see an A3, that's going to make A6 because you've got division meaning subtraction. So that's one way you go about it. If you flip them into negative indexes, it just means another line of working, which is fine, right? You can do it. but it's a bit more efficient to be able to recognize this as a subtraction law type thing. So we're still going to have the 5 cubed from before. A9 and A3 make the A6. B9 and B6 are going to make B3. And then this is where having the negative indexes can be nice. Putting this as C -6 means you have no fraction anymore to work with, because there wasn't anything to cancel the C into. This is where I like having everything in the same line. But it's totally fine if you prefer to have a divide by C6. That's also acceptable. A6, B -3, C3. Oops, let's not cut through the letters. Cool. Alright, definitely simplified from where it was. Can go further though. What else?
Wouldn't it be easier to write the division as a fraction instead?
I think so, yeah. So do you mean putting the fraction under here, or do you mean doing like a 1 divide this and making it times?
No, like putting it under. Well, you could do both ways, I guess, but
Yeah, well, that's what I'm saying. You can do both. I'm curious which one seems easier.
I'd say putting it under would be easier.
Sure, certainly. So that means we're going to have 5 cubed A6 B3 C -6. Yeah, I'm trying to think. If you're going to have it under, you might want this C -6 back down there, but I guess it doesn't really matter too much. Then A6 is going to go down here. B -3 is going to go down there. C3. Now, I have just done that. I'll point out, when playing with negative indexes, it's pretty common in the private classes that I run where people will immediately assume that negative index means it goes down here and becomes positive. And in this transition, it's a common error to take this B -3 and make it B +3 because they think, oh, I'm flipping it, it's going down. In reality, this was already on the denominator. All we're doing is literally just rewriting it because division means denominator. So just keep that in mind if that was a thing you were curious about doing or inclined to do. Cool. All right, pretty much almost done here. Only really one thing left to do. Maybe someone can just say the final answer, or at least tell me what the steps would be.
Subtraction.
Subtraction, yeah, absolutely. So at this stage, since we're basically fully simplifying things, we could expand the 5 cubed out to be 125. A6 and A6, well, cancels, nice and easy. B3 and B -3. Now remember, when you do the subtraction, it's numerator subtract denominator. So it's 3 minus -3, making it 6. And then in this case, you've got C -6 minus 3. So finally, C -9. This is how I write my answers. I like having it all in one line because it literally looks on one line. Like if you're writing it on a line piece of paper, you don't have to use more than one line to do it. But if you prefer fractions, or if you're told to use fractions, then the other way to do it would be like this, using a full division symbol, flipping that negative index. Cool. If there's anything in there I need to clarify, by all means, let me know. Otherwise, we're just going to keep stepping up the difficulty from here. What else? What else? Actually, that's about as difficult as those particular ones are going to get. I'll pull in one that's... yeah, I think we'll do 8b for this one here. I haven't actually talked really at all about how to simplify this one, so this will be up to your own ideas on how we might go about things. 2 to the power of -3 times 8 to the power of 4 times 32 power of -3 all over 4 to the -4 times 2 to the negative 2. So yep, as I said, I haven't actually explained the more efficient way of doing this. I'm curious if anyone can just sort of come up with it themselves.
Chris, can we convert all the powers into a base of 2?
That sounds like a brilliant idea to me. Yeah. So the fundamental there is that whenever we're doing index laws, literally all of our index laws require that the things we're using have the same base. Otherwise, they're just not index laws anymore. And so yes, these all have a common base. What's that common base?
2.
Yeah, 2. So again, there's the power of understanding what your powers of 2 are at a glance. Like these should all be pretty obviously powers of 2. If not, you now have an excuse to play a game, 2048. But okay, cool. So we know that these are all bases, or could be, bases of 2. How can we now rewrite it to achieve that?
So we already have 2 like numbers that are already in the base of 2, so we leave them alone.
Yep.
And so 8 to the power of 4 can become 2 to the power of 3 to the power of 4.
Yeah, that's it. 8 is 2 to the power of 3, and then we leave that power of 4 behind where it was.
And hold on. 2. Okay, so 32 becomes 2 to the power of 5 to the power of negative 3.
That's good, yeah. And that was quick as well. Nice. It's a quick conversion from 32 to 2 to the power of 5.
And then 2 squared to the power of negative 4, and then the other one is already in the base 2.
That's it, yeah. So yeah, you just go through and figure out, okay, 2 to the power, what gives me that? 2 to the power, what gives me that? So on and so forth. Not forgetting that those did have powers associated with them before, which is why we still got these cascaded powers going on. Awesome. All right. We all have same bases now, so we can go wild with our index laws. What can we do from here?
We simplify the numerator and denominator. I think
Yeah.
from a glance, the denominator looks like it will be 2 to the power of negative 6, maybe.
2 to the negative 6? Maybe. Let me have a look. Okay.
Because there's negative 15,
To
positive
the-
12, and negative 3.
Wait, hang on, say again. What have you got?
So what there's negative 3 on
Oh,
the
you're
top.
pulling this one.
Yeah. And there's to the power of 12, so that becomes 9. And then we've got negative 15, 2 to the power of negative 15 for the third term numerator.
Oh, okay, so you've just done the whole... Okay, sorry, I thought you meant you were doing denominator. And yeah,
No,
okay.
no, I'm doing numerator.
Yeah, all good. So I'll just sort of spell that out in a bit more detail. We got 2 to the negative 3. Handling the cascaded powers, you got 4 3s are 12, so 2 to the power of 12. And this one here, this is 5 and negative 3 for 15. Oh, negative 15, sorry. 2 minus 15. And you'd probably also do the exact same thing to denominator first. So 2, negative 8, 2, negative 2. And then from there, like these numbers obviously look like painful to work with if you were to expand them out normally. Just doing your addition law because it's multiplication is going to be a much easier approach. So 12 minus 15 minus another 3, you're looking at minus 6. Yeah. 2 minus 6. Yeah. And then on the bottom, minus 8 and minus 2 is minus 10. And well, from here there's a little bit of a trickiness with your negatives. But remember, you do negative 6 minus 10. So you're looking at 2 to the power of 4. Which, someone can tell me, what's 2 to the power of 4?
16.
16. Yeah, good. So yeah, I mean, being able to easily just go 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, like being able to do all those and just rattle them off immediately, you'll be able to count these real quickly, and it comes in handy more than you might think. Okay, cool, that's that one. We'll do a slight variation on that, just to see how you handle it when it looks a little bit different, which is 5 power of 2n times 10 to the power of n over 8 power of n times 5. And it's also 5 to the power of n. That's better. That's 8c for those who are using the screen share or the textbook. Looks similar. What could we do? What's stopping us from doing exactly what we just did before? They look like the same question, right? We got some numerical bases and some unknown. Well, I guess this was fully numerical before, but it's still a similar vibe where you got number bases and then some powers. Why can't we just do what we did before?
Chris, they have different bases, but at least for the like numerator, can we factorize possibly? Factor an expression out?
Yeah.
Like
What's that going to look like?
maybe yeah, so we take out 5 to the power of n
Okay.
from the two expressions, so you get 5 to the power of n times 5 to the power of n times. Hold on.
Yeah, that's a bit tougher to see in one line. I reckon you'll still be able to do it. You're skilled.
Just times 2.
Times 2.
Oh, actually, no, hold on.
I think it'll be 2, but something's got to be on there as well.
2 to the power of n.
2 to the power of n. Yeah. That's real tough to see, so I'll just do this across here. The proposed way of going about this is to actually still do the same thing we did do before, but we're just going to be aware of the fact that we won't always get everything into the same base. There will be some common bases, there will be some uncommon bases. It's like having x's and y's. We're just having 10s and 5s and 2s in this case. So essentially, that is correct, yeah. To break it down in a bit more detail, you would have 5 as a prime number, can't do anything with that, leave it as is. 10 is not a prime, but it can be broken down into 2 primes, which are 5 and 2 respectively. 8, not prime, that can be 2 to the power of 3, power n, and then 5, power of n. All of a sudden, we've got 5s and 2s that we're working with. So where this one came from was being able to distribute this n through both of these. And then, yeah, you can take it out as a common factor. It's probably easier to sort of just leave them as their as the string of multiplications, though. So you have 5 2n, 5n, because you bring this one into here, and then 2 power of n from that one. Lastly, you have 2 3n from combining these via multiplication, and then you have 5n, which was just what it was before. Now, I mean, whether you took it out as a factor or not is kind of... Yeah, actually, maybe that didn't work properly, because in this case, you'd have to have... I'm trying to think what we had before. Because if we just had like 5n out here and 5n out here, there needs to be like a +1 that would have been left behind. So I think something was a little bit off there. I don't know. Point being, we're here now. Here's much easier to see, because now you got 5n, 5n. They cancel down really easily. And you got 2n and 2 to the 3n. So you're still going to have that 5 to the 2n from before. N minus 3n, you're going to have 2 to the 2n, like that. And then that's just going to be your answer. There's no simplifying from there. Maybe
Chris,
if you...
Can't it be 25 to the power of n over 4 to the n? Because we can separate the powers.
Yeah,
Or
yes, so you could.
is that like not? Is there really no point of doing that?
I would say it's a slight unsimplification because you're using bigger numbers than you need to. Like one thing you could do to go a slight amount more simpler would be actually factor out the 2 to the power of n across both. So you have 5 over 2, and then all of that's the 2n. I guess one of the rules of simplification is the least number of digits, or just like pencil strokes, to write an answer is probably the simplest it can get to. So if I were to say what is the actual simplest form, probably this right-hand side, but this will also get you there. Bringing the square in through both and making it 25 over 4, doable, but you're now adding an extra digit in there. I think this probably demonstrates more understanding of the index laws, and I think that's kind of what you want when you're doing your answers. You want to demonstrate the most understanding as you possibly can, depending on how high you're shooting for marks, obviously. Like, I think both of these will give you full marks, but you know, if you're shooting real high, this final line here demonstrates you understand things better than if you had just done either leaving it on the left-hand side or bringing that 2 in, which I guess bringing the 2 in does demonstrate you know how to do that. But I'll default to the previous explanation, which was that you're adding another digit where it doesn't need to be. Is that a fair enough explanation? I feel like I kind of went on a tangent there. Either way. What else have we got? So we've looked at how to do that's a technique called prime decomposition, by the way, and it works for stuff that's not just your index law stuff, or at least stuff that's not nominally index laws. I've seen it be really helpful for simplifying, I think it was binomial probability. Because with binomial probability, you have fractions and powers, right? Because you have, I won't get into the specifics, but you have fractions with powers in them. And some, especially recently with some of the tech-free exams, they'll give you some pretty nasty numbers. And it turns out to be the case where using this in non-exponential stuff, like using it in probability, and anytime you have powers and bases, it's actually a really solid way of simplifying those without having to put in too much pain of solving things. So the techniques here definitely have made at least my simplification efforts a lot easier, and that's coming from someone who had graduated and then 4 years later looked at it and realized, oh, here's a better way of doing it. But yeah, okay. There's a whole bunch of stuff there. Let's see. Yeah, I reckon we've got time to squeeze one more of these in before we look at fraction powers. I think I'll just simplify it down just so we can get the gist of it, which is, what if I have something like a to the power of 2n minus 1 divided by a to the 3n plus 2. So nothing's actually conceptually different here, but I know for a lot of people that looks tough because you don't have just a single sort of power. You've got additions and subtractions in there as well. You don't actually do anything different though. Can anyone tell me how this will simplify?
So like what I like to do at least is to just disregard the a's.
Yep.
And then so we write 2n minus 1.
Mhm.
And then we put a negative sign and then brackets 3n plus
Yeah.
2.
Great.
Just so like we remember to distribute the negative.
Brilliant.
And then we just solve this as using our normal algebraic skills.
That's it. That's correct, yeah. So that's exactly what I want to highlight, which is when you're doing division, it's always this thing minus this thing. And so using that bracket, really, really good idea. The other thing that I've found that could be useful for some people is, I know some of you like to do substitutions. So, I mean, it's going to be a bit heavyweight here, but I'll just show you just in case you're at all curious. You can literally, like, if this is a nasty complicated thing, you can just call this thing B and this thing C. And so now you're just looking at a to the power of b over a to the power of c. That's very clearly just a to the power of b minus c. And then from there, once you put in your b and c, it'll then look like that. Bit more heavyweight, Wouldn't necessarily recommend it, but some will like doing that. Up to you guys, of course. Whatever makes it easier. That's all I really wanted to share there, how you handle when there's more than one term in there. You want to make sure the subtraction applies to the whole thing, not just the leading term. All right, capping it off, let's have a look at some rational indices. Let's see, where's a good place to start? Nothing's really different with rational indices. You're just multiplying and dividing, subtracting fractions rather than integers. We'll give it a test on at least one of the simpler ones, and then we'll see how to work with when it looks a little bit different. So a to the power of -2, b all to the power of 3. That's going to be multiplied by 1 over b -3, and that's going to be to the power of a half. Okay, what could we do?
Chris, you know the second brackets?
Yep.
Could we just like flip the b to -3 to like a positive indices? Because on top there's only one, right? So that might just make it a little bit easier.
Yeah, no, I love doing that. That's a great idea. And just to elaborate on that, it doesn't even matter if this is a 1 or a 2 or a 3 or whatever. If there was another number in there, like let's say it was a 3, it just means that now you have 3 b cubed because you're putting it back up. So all that to say, don't necessarily worry about if there's another number there. Oh, I should probably stop pressing that undo button. Looks like it's crashing the whole thing.
Yeah, and then we can just like we can obviously do the first bracket, which is a to the -6 and b to the 3.
Yep. So that's like one of the first things we looked at, which is how to distribute the powers. Yep.
And then the second one becomes b to the power of 3 over 2.
Yeah, that's it. So you have cascade of powers, it's multiplication. You now just need to be familiar with your fraction multiplication, which, yes, is 3 over 2. b 3 over 2, a minus 6, b 3.
And yeah, this is just like we now just distribute it into the brackets.
That's it, yeah. This will require you to understand how to do fraction addition, because remember when you have bases multiply, it's addition. So you're going to have 3 over 2, sorry, yeah, 3 over 2 plus 3, so you're looking at 6 over 2 plus 3 over 2, so that's going to end up being 9 over 2. So if your fraction math is holding you back, please, for the love of God, go back to the linear chapter, swallow the pride, and just practice it because you'll need it, right? Like, no one's going to know. Just, I know a lot of you have trouble with fractions. Just practice them. You'll get there. And I've got, in fact, yeah, I've literally got guides that you can refer to as to how I handle fractions. What I'll do is I'll actually just put it in there, which is the review of algebra. Cool. It's that one. But anyway, that's that. Now, probably one of the last things we'll have a look at will be testing your remembering of how to handle this kind of scenario. I've kind of only implied how to handle it. I haven't, sorry, no, I've said how to handle it, just not how it looks in this particular case. So this will unblur in a moment. I'll fix that up, don't worry. Divide root a b cubed. Come on, wake up. There we go. Cool. We've got roots there. How do we handle roots?
Can we convert the roots into indices?
That's exactly right. Yeah. So the test here was, of course, remembering that fractional indices are roots. So what's that going to actually end up looking like? When you've got a cube root here, how do we make that into?
So a squared times b in brackets, and then outside the bracket you put 1 over 3.
That's it.
The
Yeah.
power.
1 over 3. So any root that you have becomes a denominator of the power.
And then I would personally do a multiplication straight, like multiplication 1 over AB cubed, but yeah.
Yeah, we can do that. That's fine.
Yeah.
1 over
Over AB cubed to the power of 1 over 2.
1 over 2. Yeah, cool. So even though there wasn't a 2 that was written there, we got to remember that square root is implied in the case where there's no number associated with it. Yeah, and of course remembering that any division of things, it can be the same thing as multiplied by 1 over that thing. Cool. What else?
When we're simplifying, I believe we can subtract the exponents. No, we can't.
It's a bit early for that one.
No, we
Yeah.
can't. So maybe we distribute the exponents.
Yeah.
first.
Distributing first. So pretty much in order of operations, and I kind of detail this in the work solutions that I provide at the start, which is in order, pretty much you handle the cascaded powers. So like your power of a third, power of a half, you handle those first. Then you handle your negative indexes. I like to make them all positive. And then you do your addition, subtraction, multiplication, division stuff. That's usually the order of operations there. Not the only way to do it, of course, but definitely you should have at least a system of doing it. Whether you use my system or another one is totally up to you. I would even go as far as to say, look, you're doing multiply of 1 over something, you might as well just put it in the denominator. So that way it's more directly comparable from top to bottom. So a power of a half, b power of 3 over 2. Yeah, that's that one. And well, from here, what's the last thing?
We subtract the powers using our fraction arithmetic.
That's it, subtracting powers, which of course is kind of sucky, but we'll make do. So we got a2 over 3 minus half, and we got b1 over 3 minus 3 over 2. So we're now looking at doing a quick cross multiply. So we're looking at 4 minus 3 on 6, and then we're looking at b2 minus 9 on 6. Finally, a 1 over 6, b 7 minus 7 over 6. You can leave that there, you can make it a fraction, up to you on how you want to go about it. You could even make it a root, so that kind of flies in the face of when I said less strokes is better, but it's still okay. I don't know. I mean, writing the 6th root of a and then times the 6th root of b to the minus 7, or even flipping that as the index. Yeah, I don't know. Just my preference is to stick here. There's obviously stuff you can do to rewrite it to your own preferences, but that's where I would personally stop it just before that last line. I mean, yeah, that's pretty much all the unique. Oh, actually, there is one last cool one to have a look at, and it almost doesn't even look like an index law question. It's because it's kind of not, which is 2x minus 1 root 2x minus 1, and it's simplifying that. If you have a look at the full chapter, you'll probably notice a pretty common thread that's across all of the chapter 3 questions. Oh, sorry, the section 3 questions.
Can we rewrite the indices again as 1 over 2?
Yep, certainly part of it. You got 2x minus 1, and then you got 2x minus 1 power half. How's that simplify? We don't normally have bases that have like pluses and minuses separated in them.
I think this might be wrong because of the BODMAS laws, but I don't like. I'm just asking, is it possible to first do the brackets, like expand the brackets and then apply the indices, or can we not do that?
Probably possible. I don't
Can I
actually
check
know
if
how.
there's like a multiplication or if that's like brackets.
Yeah, I mean it is multiplication, right? Like in the sense, like how normally you would have like I don't know x plus 2, x minus 3, how you would do like all this stuff multiply across. I'm pretty sure there's an equivalent of that when there's a power of a half associated with it. I feel like there's something you can do with that. I haven't bothered to learn it because it's not actually particularly needed for this kind of thing. Here's a thought. What if I just said this was a and then times a to the half?
Okay.
How do we do that?
It just becomes a to the power of 3/2.
So basically the lesson there is it doesn't actually matter what these are, as long as they're identical to each other, index laws apply. So if I had literally written a equals 2x minus 1, that's what you would get here. And then you realize, oh shit, there it is. A 3/2, which of course a is 2x minus 1. And so then you have 2x minus 1 to the power of 3/2. So I wouldn't actually go out of my way to write a in both of them, because chances are, if you're doing that, you already know there's a common factor, so you're kind of just writing another line for no reason. That's more so me just sort of showing you that these are... It's kind of like how grouping is taught, where if you have... It's like the factorizing method of grouping, where you have like, I don't know, 3, 2x minus 1, plus 6, 2x minus 1. You've got a common factor of 2x minus 1, which can be brought out the front. And then, well, of course, you'll have 2x minus 1, 3, and 6, so on and so forth to simplify that. Exact same idea. That's pretty much it. I'm not seeing anything else in these chapters it's worth really talking about. We kind of already discussed how if you have those fractional indexes, better to root first and then, like when it's numerical, better to root first and then power up later, just because it's easier numbers. And yeah, I don't think there's really anything else to talk about here. So unless there's any further clarifications you'd like me to go through, I can save you 2 minutes in your day. I'll leave you to it.